Hi, well we're going to start doing problems from our gas law unit. All right, so we looked at the relationships in class yesterday, but now we're going to look at the mathematical relationship. The pressure-volume relationship is known as Boyle's law. And from class, we learned that pressure and volume are inversely proportional to one another. And what that looks like in an equation is P1 V1 is equal to P2 V2. So this 1 over here just means that this pressure goes with this volume, and the 2's mean that this pressure goes with that volume. Now your units, as long as your pressure units are the same on both sides, you're good. As long as the volume units are the same on both sides, that's fine as well. You are going to know 3 of the 4, and you're going to be asked to solve for the 4th. So let's do an example problem. You have 5 milliliters, that's a volume, of a sample of neon gas, and the pressure is 1.5 atmospheres. So that pressure goes with that volume. They would like to know what the new pressure would be if the volume of the gas was decreased to 3 milliliters. So that's V2. Our volume units are the same, so that's really good. All right, well, our volume went down, and so we're expecting the pressure to go up because they're inversely proportional to one another. So our pressure should be greater than 1.5 atmospheres when we're done. So let's go ahead and set this up. P1 V1 is equal to P2 V2. And our P1 is 1.5 atmospheres. Our volume is 5 milliliters. Our P2 is what we're solving for, and our new volume was 3 milliliters. So when we go ahead and solve for P2, it's 1.5 times 5 divided by 3. We come up with 2.5 ATM. And really, we should only have 1 sig fig because that was a 1 sig fig and 1 sig fig. So we'll go ahead and round it up to 3 atmospheres. And did our pressure go up? It sure did. It definitely went up. All right. So there's a law called Charles's law, and that is the volume-temperature relationship. And remember, they were directly proportional. And Charles' law looks like this. V1 over T1 is equal to V2 over T2. Now, what's important here is the temperature must be in Kelvin. The volume, as long if you're using liters on one side, it should be liters on the other side, or milliliters, just so the volume units match. But the temperature unit has to be Kelvin. All right, so you have 10 milliliters of a sample of carbon dioxide gas. That's V1, and it's at 23 degrees Celsius, so that's T1. The gas is then cooled down to T2 to 5 degrees. What is the new volume? So we're solving for V2. All right, we are cooling this down, and so our volume should go down. So V2 should be less than 10 milliliters. All right, the first thing we have to do is V1 over T1 is equal to V2 over T2. We have to convert these temperatures. So T1, it's 23 degrees Celsius, and so that is 296 Kelvin. We're adding 273 to it. And T2 is 5 degrees plus 273, which is 278. All right, now that our temperature is in Kelvin, we can go ahead and plug our numbers in and solve for our new volume. Okay, well, we started off with 10.0 milliliters, and our temperature was 296 Kelvin, and we would like to know what our new volume is when we have cooled this down to 278 Kelvin. So the algebra here is I cross multiply, so we get 296 times V2 is equal to 10 times 278. And then when I solve for V2, V2 is 9.4 milliliters. Did our volume go down? It did. We cooled it down and our volume went down. Really, that should be to 1 sig fig because there's only 1 sig fig here, so we could call this 9 milliliters. All right, now there's something called the combined gas law, and this is the equation that's given to you on your reference packet, and it's a combination of Boyle's law and Charles' law, and it looks like this. And really, this is the only equation you really need to know. If we were doing Boyle's law, remember, temperature remained constant, so it's like the T's are just a 1. And in Charles's law, the pressure remains constant, so it's just as if the P1 and the P2 were a 1, and they don't appear in the equation. All right, guys, let's try a combined gas law. Now, we have a flexible container, and our volume is 15.9 liters to start with. This pressure is in kilopascals, so that's our P1, and here is our T1. So those all go together. Then the pressure changes to STP, and they would like to know the new volume. Well, standard temperature is 0 degrees Celsius, or 273 Kelvin, and standard pressure, well, we have to make it match this pressure unit. This is kilopascals, and so you look on your reference packet, and the standard pressure in kilopascals is 101.3 kilopascals. So that's our T2 and our P2. Now we're ready to plug our numbers in. All right, now our P1 was 589 kilopascals. Our V1 was 15.9 liters. And our T1, well, we have to convert that 56.5 to Kelvin. So our T1 is 56.5 plus 273. And our T1 is 329.5 Kelvin. All right. Now, that is equal to P2, which is STP, it's standard temperature, it's 101.3 kilopascals, times our V2, which is what we're solving for, and divided by our temperature, which is 273 Kelvin. All right, the best way to solve this is to cross multiply and then solve and set them equal to one another and then solve for V2. So when I do that, I come up with my new volume being 76.6 liters. So I multiplied 589 times 15.9 times 273, and then I set that equal to 329.5 times 101.3 times V2. Then I took the product of this and divided it by the product of 329.5 times 101.3. And my final answer is 76.6 liters. Well, as you can imagine, we are going to be practicing this in class, and so I hope you understand how to solve these problems, and we'll see you in class tomorrow.